Hello everyone, and now welcome to this class, and which earlier we were discussing this central potential or central potential scattering, and in which we have calculated some formulas which gives you the differential cross section and the scattering angle in terms of the impact parameter. Try to learn that about the solid angle, what is impact parameter, what is scattering angle, what is flux, what is intensity, and now we are going to apply those formulas into calculating the scattering cross section of the Rutherford scattering cross section. Okay, so now in case of Rutherford scattering cross section, what we have, we consider the scattering of the charged particle, that is basically is going to be the alpha particle of mass m, and that charged particle is having a charge of z prime e. Okay, and into the Coulomb fields of some heavy nucleus whose charge is Ze. Okay, the nucleus is assumed to be at rest during the collision. That means we are working into the laboratory frame. So this is at rest, and then I have a particle coming towards its in the field of this particular target, which is at rest. This is the nucleus, heavy nucleus. So now let us have the idea of scattering with the charge this z prime e, and the incident particle of charge z prime e is how they are going to interact with each other. So we know that this is of charge this, and this is of charge this. So we can write the force acting between this is going to be the Coulomb force, and this is 1 upon 4 pi epsilon naught. This is z prime e square, and e square, and then this is r square. So this is say k consists of, so for the calculation purpose, because this is constant, I am not going to consider it in any further in the expression. So I am going to, my k is simply minus z prime e square. Okay, so this is because this is force is attractive, Coulomb force and central force. So the charge particle, because the charge particle is moving in a central force field, so we have the equation of the path we already have calculated. If you know, this is 1 by r mk square. This is my eccentricity, because when the charge particle is moving in the central force field, that is going to be either ellipse, hyperbola. Okay, so depending upon what is e, this factor, the trajectory or the orbit is going to be decided. So this is the general formulation, that if a charged particle is moving in a central force field. So let us try to look into, in this case of when alpha particle of charge z prime e is going to towards the target of heavy target, which is having a charge of Ze. So before that, let's try to see what is happening here. So as the particle approaches the nucleus, so this is the particle of charge z prime e, which is approaching the nucleus from infinity. So what is the force direction? This is a charge particle, this is a charge particle, this is a charge particle. The force is, the central force is acting along the line which is joining these two. Okay, joining these two. This is what this r is, red r is. Now the particle is coming, and this repulsive force, because this is positive charge, this is positive charge, so they are going to repel each other. So the repulsive force increases rapidly, and the particle changes from a straight line path to hyperbola ADP. So when the particle is coming, and that is, as it going to close to it, the more repulsive force is going to act, and this particle is going to repel. So this particle is coming, and then this is getting repelled more strongly along this direction. Okay, from coming from some infinity and then going to this direction around the parabola ADB. This ADB having one focus at this position, and this is one of the focus. So the asymptote, when you draw an asymptote, so how you draw asymptote along this scattering line. From here you draw an asymptote. Okay, and where these asymptote meets. Okay, so this is what you have. They meets each other. Okay, so then you have this scattering angle theta. So this is AO and BO, this is AO and this is BO to the hyperbola give the direction of the incident and the scattered particle. So the angle COB, this is angle COB is going to be the scattering angle, and NM, this is my M, this is NM is going to be my impact parameter S, because this is the particle coming. If it is not being deflected, so it is going to follow this straight line. Okay, and if you draw a perpendicular from center of force to this, so this is going to be the impact parameter. Okay, so and this is a straight line when the particle is coming straight, and then from here it is deflected, so angle between the incident and the deflected ray is going to be your scattering angle. Okay, so this is what angle is psi. We have already discussed that angle between the periapsis and the incident direction. So this is what I have. So this angle and these angle are same. So what is going to have? So this is what is happening. So we can use this, and I told you that the general formulation is 1 by r, it is mk square, where this is my eccentricity. Okay, so please don't get confused with this E and this E. Okay, so I am going to write this eccentricity is epsilon. Okay, this is my epsilon, not E. So E is here is charge. Do not get confused with this. So do not get confused between E and E. One is this is charge, and this is eccentricity, or say where this is eccentricity. I would have been use the different notation. Okay, now this is my eccentricity. I can write this mk. K is my k is my z prime e square. Okay, so this is my z prime e square. Here is mk. M by l square is there. So I have 1, and this is my eccentricity. So this is my eccentricity, and then cos theta minus pi. So I'm getting theta 0 is pi. Why pi? Because it's coming from the infinity incident direction. So this is why I'm taking it pi. So eccentricity is this much, and if I put this twice e l square, k is z prime e square. So this is z square z prime square e4. Okay, divided by m. So now taking theta naught is pi. So when this is cos theta minus pi is minus cos theta. So this becomes this angle becomes minus. So I have this. What I'm going to have is, okay. So cos theta. What is happening? It is okay. So one is okay. This k 1 minus will come from here. Okay, so that becomes this minus, because the k is minus z prime e square. Here is a square, so this is going to be this, and this k with this negative sign will make it e cos theta minus 1. So because this is going to be 1 minus epsilon, this is my epsilon eccentricity e cos theta. So if I have already 1 here, this become this minus becomes e cos theta minus 1. Okay, this is correct. So this is one thing we have. And now this relation between this angular momentum and this impact parameter and E, we had already discussed that, equating the this angular momentum and this kinetic energy. So this is L is equal to twice under root twice me. Okay, so I'm going to use I'm going to put this into use this into here in this eccentricity formula. So if eccentricity formula is twice e l square, z square e4 by m, so I can use that l square, because l is s twice me. Okay, so l is you see twice me, so I'm going to use it here. So this is going to s twice me, twice me. This has to be a square of this. Okay, square of this. So then becomes this is again, this is 4, so this is twice e, and this is s square twice me. Okay, so it becomes 2 to 4 and e square and m. So 2 to 4, then twice e, s square is also there, so we can all get, because this m and this m will cancel out, so I have twice e s, that is it square, z prime e ka whole square is there. It's fine. So obviously this eccentricity, this epsilon in our case is going to be, epsilon is going to be 1, because this is 1 plus all the quantity here is going, not is going to be, either is going to be negative, then is also going to be some square of this. So this is going to be always greater than 1. So that propose that this orbit is going to be hyperbola. So because if eccentricity is greater than 1, the orbit is going to be hyperbola. We already know this. Okay, so now one thing is definite, that in this scattering the eccentricity is going to be is greater than 1, so it's going to be the hyperbola. So now this is the hyperbola path must be symmetric about the direction of the periapsis. Okay, that is we already discussed. This is my periapsis, the closest approach from the center of the force, that is what your periapsis is going to be symmetric. So that's why we have scattering angle is pi minus 2 psi. So psi is the angle between the reflect the asymptote of this from the direction of the scattering making with this periapsis. Okay, so then psi is pi by 2 minus theta. So this we already discussed. Now the important thing here is that the asymptotic direction, because when r is going to infinity, so then theta is going to psi. Hence equation 5, in this equation 5, which is what is my equation 5? This is my equation 5. So this theta we are talking about, this theta. Okay, so this theta is what? This theta is if you consider this theta is after the scattering, what is the angle of the incident particle. Okay, so when r is infinity, so what is infinity? You see that when r is infinity, then theta is going to be psi. Hence from equation 5. So what do I mean by this? That for the asymptotic direction, the r, that is for which r is infinite, the theta is going to be psi. So earlier it is theta is pi. Okay, so then if it is going to be infinite direction, if it's going to be r is going to be infinity, so after the scattering, if it is going to be infinity, okay, so naturally that what you're going to get is, earlier it is going to be in a straight line, if not being deflected, and then if it's going to be infinity, so what you're going to get is this is going to be after scattering, there's going to be infinity. If r infinity, then this, if you draw a line, draw a scattering angle, from this, is going to be equal to psi. That theta is going to be always psi. Okay, so then if in that relation of cos theta, that cos theta is different from this scattering angle. This you have to be careful about, because that theta is related to this psi angle, because this is the angle which the particle is making. The particle asymptote is making with the closest approach. Okay, try to understand this. Okay, so as r is going otherwise this is going to be like, this is going to be pi. Okay, when this is going to be infinite, and this is going to be always as r intending to infinite, this is asymptotic range may, then as it going to come here, then always that angle is going to be equal to pi. That is the angle made between the periapsis and the asymptote of this. Okay, so normally what you see that when this deflection is very less, around this, so then this can be this can change. But when it is at large distance, this is always going to, as r tending to infinity, this is always going to equal to psi. So then if I put this into the expression, was this is what 1 by r, some constant was here, and then I was having e cos theta minus 1. So then when r is infinity, so this is going to be c, that is going to be e cos psi minus 1. Okay, so this is going to be 1 upon infinity is going to be 0, so I have e cos psi equal minus 1 equal to 0 from this case. Okay, so at r tending to infinity, the theta is going to be by psi. So this cos psi is 1 by e, and then because psi is because scattering angle, that is going to be pi minus 2 psi. So I can now relate this in terms of this psi is pi by 2 minus the scattering angle minus 2. So now this is scattering angle, this is not this angle theta. Okay, so this is pi by 2 minus theta by 2. So cos of pi by 2 minus theta is going to be sine theta by 2 1 by e. And then I can write this is 1 upon sine theta is cosec theta is going to be e, and cosec square theta is, if I square this, is cosec square theta is going to be e square. And then e square minus 1 is cot square theta by 2. And these are basically, if I say this is my epsilon, so let us write epsilon here. So these are my epsilon, eccentricity we are talking about. So these are epsilon, so these are epsilon, these are epsilon, these are epsilon, epsilon square, these are not the charges, these are the eccentricity. Okay, this is the charge. Okay, so because now this, we know that this is equal to this, so that's this 1 will cancel out when you square this, you have twice e square. So now cot theta and the scattering angle and this impact parameter and the charges of the target and the projectile are related using this equation. So from here I can find what is the value of s. So that is going to be z prime e square by twice e, that is cot theta by 2. Okay, this is the impact parameter in terms of this scattering angle. Okay, so this is what this is. I have z prime e cot theta by 2. Now because we had to find this sigma scattering angle, that is going to be s upon sine scattering angle, and then this is ds by scattering angle. So for that, this I know already in terms of this, so I have to find s ds by d theta. Okay, so I can find ds by d theta because only the cot theta is because s is z prime e square by twice e cot theta by 2. So I can have this differential to the cot theta, and cot theta is minus half cosec squared theta. So this is half becomes 4, and this is what I have, this is cosec square to theta. So which get rid of negative sign because I am doing in this mod experiment in mod quantity, that is going to be s and theta dependence. So if I substitute this value in this equation, okay, in this equation already written here, so so s I can put z square by twice e cot theta, and then this is 1 upon sine theta, and then this quantity is this we have calculated here. You put this all together, so I can write sine theta is 2 sine theta by 2 cos theta by 2, and I can write cot theta is cos theta by 2 sine theta by 2. Okay, so if I write this as cos theta by 2 divided by sine theta by 2, so this cos theta will get rid of cos theta, and then I have 2 sine square theta, and then this is going to be cosec 4 theta. Okay, it writes cos theta by 2 and sine theta by 2, so this will cancel out. So I have sine theta by 2 and 2 square this, and this is going to be cosec 4 theta by 2. So this is the differential scattering cross section in terms of the Rutherford scattering of the charge particle z prime e, and the target is of charge z e and z prime e. Okay, so these are all independent of the number of particles and the mass and all these. Only the cross section depending upon the energy and this scattering angle theta. So you can see that this is well known expression for the Rutherford scattering cross section, and the scattering cross section or the number of the particle scattered per second along the direction of this scattering theta are proportional to, you can see, is fourth power of the cosec theta by 2, and this is a square of the charge of target and incident. This is what we have, a square of this charge and incidence, and inversely proportional to this energy. Okay, a square of the kinetic energy. So, and also you can one more comment is here, that it's interesting to note that it increases very rapidly for a small angle and even becoming infinity at theta equal to 0. Okay, so this is how cosec is cosec theta is 1 by sine theta. Okay, so how this is cosec 4 in fact. So if theta is 0, so this is cosec theta is sine 0 is 0, so this is going to be infinity. So at theta tends to 0, it becomes infinity, this. Okay, that means when the scattering angle is 0, this differential scattering cross section is going to be infinity. And if you do the total scattering cross section, if you do the total scattering cross section, this is also going to be infinity. You can calculate this integral, but this is definitely going to be infinity because we obtain infinite result. Why? Because the physical reason behind this is very important. So this is a Coulomb field. So if I have a particle is coming, so if particle is coming towards this, and so that's, if this is a plus charge, and this plus charge is coming towards this, so this will be get deflected. Okay, or if the second this particle is here, if this will also get deflected, but with some different angle. Okay, this will be angle of this will be angle of this. But if a particle is here also, if this plus charge, or here also this plus charge, this is going to be get deflected. Whatever this particle is here, this is also, if this is going to have, this is going to be deflected. Okay, this particle here, this is also going to be deflected. So if you state from minus infinity to plus infinity, all the particle, wherever the charged particle which is in this field of this, if you overall integrate it, then this is going to contribute into the scattering cross section. Okay, so that's why it's going to be infinite. So the very small deflection occur only for the particle with very large impact parameter. So whatever this impact parameter is this impact parameter is this, his impact parameter is this much. Okay, so whatever the impact parameter, depending on impact parameter, the scattering the deflection is going to be very small, but that is going to contribute anyways. So from minus infinity to plus infinity, because you know the Coulomb charge, if two particles are at infinite distance, the charge deflection, the effect is there, Coulomb force. So that's why it's going to be infinity. Okay, so this is scattering cross section in case of the Rutherford scattering. Okay, and let me now uh, discuss one more thing. Okay, so now we'll move to another important concept. This is we will discuss a little bit here in this class, and then we will discuss in detail into the next class, that there's a transformation of the scattering problem to laboratory coordinate to the center of mass. Okay, so we had to need to establish the relationship between the center of mass and the laboratory coordinates. So you know that in laboratory coordinate system, what you have, there is a one incident particle moves and in the and the scatterer is at rest, the target is at rest, and this particle is moving. Okay, so one of the target or is going to be at rest, and then this is like in Rutherford scattering, the alpha particle is coming, and this gold foil is at rest, and then it's going to hit, and then it is going to be reflected and crossing whatever it is, depending upon the dynamics and and the forces which are acting. So this is what the laboratory system is there. So we actually experimentally what we measure is we measure in the laboratory system, where this is the scattering angle theta. This is scattering angle theta. This theta is written differently. Here you can see that this theta is written as like this. Okay, this theta is written as like this, and the earlier where scattering angle was this. So this is for the different purpose. Okay, so you had to be careful about this. So the scattering angle, because the particle is coming and it is scattered from the center of force, and then if you draw a asymptote and then where it cuts, this is your scattering angle. Okay, so the scattering angle actually measured in the laboratory is which is the angle between the final incident direction of the scattered particle in the laboratory coordinate system. So if I see this is you have one particle here and then another particle is here. So this is the first particle, this is my second particle. So depending upon this, the second particle here in this case is my target itself, because it may happen that if I have a particle here, a second particle, and the first particle comes from here, and it is when it comes here, and then it is get deflected from its path, but this particle, because of that repulsion, that's also get recoiled in certain direction. Okay, so this is what is happening in the laboratory frame. Earlier this particle is at rest, but because when the particle comes here and then the Coulomb force is being exchanged between these two, so this field more Coulomb charge because of the less mass, and then less charge, and so this is going to scatter more, and this is going to because of the recoil it can also go to some direction, and that the vector which is joining these two, this is r, is the angle between these two. This is written as theta. Okay, so this is related with the center of mass kind of thing, because if in the center of mass system what is happening, a particle is coming from here and particle is coming from here, they are coming towards each other. Okay, in the center of mass. So this is center of mass is always at rest and taken at the origin. Okay, this is always at rest here, and so one particle is coming in one direction and the second particle is coming in the second direction, and then they come towards each other and then repel each other. Okay, like this. So one is not stationary like this and come and then it's go, and because of some recoil it comes, but it is happening, this is coming, and then this goes this way and this goes this way. So this is what this is repulsion is there, center of mass. So before scattering, the particle are moving directly towards each other, and afterwards they will moving directly towards away from each other. So the momentum is getting converged in center of mass system. Okay, momentum is always going to be zero. So in this system the total linear momentum is zero, because when a particle is coming here, plus and minus momenta, and then go with in opposite direction, the total linear momentum is always zero. The two particle moves away with equal and opposite momenta, and the angle theta is calculated from the equivalent one body problem, is the angle between the final and the initial direction of the relative vector between the two particles. That is what the relative vectors between the two particles, as this is what you can, this is vector. So if you draw this vector, so this is going to be, this is theta, angle between the scattering of this particle and this particle. The same analogy you can see that when this is at rest and when particle comes and then it goes away, scattered, and because of some recoil it goes in this direction. So this vector which is between these relative vector between these two particles, making an angle with the incident, so that is going to be the scattering angle in center of mass frame, not in the laboratory frame. Okay, so the angle theta is calculated from the one body problem. So these two angles, this is one is in a laboratory system, one is in the center of mass, would be the same only if the second particle remains stationary through the scattering process. Okay, so if we see here, this particle if is stationary, is not moving in this direction, this is here, so then this vector shifts here, and then this goes to the same, the scattering angle and this theta is going to be same. Okay, so this whole vector is going to shift from this direction to this direction, and you have going to have this same angle. Okay, so in general, however, the second particle, though initially at rest, is itself set in motion, because I told you, because of this recurrence. So in general it happens. So the equivalent one body problem does not directly furnish the scattering angle as measured in the laboratory coordinate system. Okay, so now let us move to some dynamics that we are going to cater here in this case. So that is, you see, we are going to find the connection between these two theta, that is the scattering angle in the laboratory frame, this one, and a scattering angle in center of mass. Okay, these two you have to be careful about in writing by considering the transformation between the center of mass system and the laboratory system. So this is what I'm going to have this defined, that R1 and V1, that is this V1, this vector is in the laboratory frame, because this vector is related with this scattering angle in theta, and then prime, this R1 prime and V1 prime are the position vector and the velocity in the center of mass frame. That you can see this is theta related with the center of mass system, and then R and V are the position and constant velocity of the center of mass in the laboratory system. Okay, so this is what is V is here is given. Okay, we already know that we can be written, we will going to write this as V. For now you consider it is a V, and this is the R is there. Okay, so our corresponding position vector is R. So now by definition we can write that this is R1 is equal to R plus R1 prime, and then I can write this as V1 is V plus V1 prime. So this V1 is this, I can write this is one vector, so this is V1, so this is V1, and this is my V1 prime, this is V1, and this vector is my V. So this V, so this V1 is basically sum of this and this. Okay, so this is what we have in equation 2. So at which time angle theta and theta prime respectively, V lying in the this is lying in the stationary direction. This is what the dynamics is here. Okay, so now we can have this the second set of is PQ. So what is PQ? PQ is this is P here and Q here, this perpendicular distance. If and this is again equal to AB, this distance. So this distance and this distance, PQ and AB, are going to be, PQ is in terms of you say, so V1, this is going to be this is with this theta, this in this angle, this is going to be V1 prime sine of this angle, this is capital theta, and if you see into this angle, this is going to be V1 prime sine capital this theta. Okay, so and where is my, okay, this is not prime, because this is this angle we're talking about, this angle, sorry. So this whole angle is going to this V1, and sine this angle, this is going to be sine theta. So these are equal, this is this length and this length are equal, related with V1 prime and V1. So this is V1 sine theta is V1 prime sine theta. And then talking about OB is some OC, this OC, and then BC, this is my BC. So if you see this OC plus OB, this is V1 cos theta. OB is what? This complete OB is, if you concentrate on this angle, this is V1 and this is angle theta. So this is V1 cos theta, this is fine, this is V1 cos theta, this angle, and then this is OC. OC is what? This O and C. If you see that this OC is nothing but this length is equal to this length. So OC is nothing but this V. Okay, and then BC is what? BC is, if this is my V prime, okay, and this is angle theta, so this BC is, this is V1 prime, and cos theta. So this is what you have. So from this you can have, if I divide by, this is v1 sine theta. If I divide by sine theta, okay, if I divide by sine theta, this is going to be tan theta. So tan theta is, this is if we take the ratio of these two. Okay, so this is sine theta by cos theta, this is going to be tan theta, and v1 prime sine theta is there, and then v plus v1 sine theta is there. So if I take v1 prime common, so this will cancel out, and this I'm going to have v upon v1 prime, and this is what I'm going to have tan theta. This is one important relation. Okay, so now I'm going to stop here at this point, and in the next lecture I will discuss from here itself. So for now, thank you all.